So welcome to Generative AI in Production and Advancement track again. I'm Charlotte, working on LLM inference at Meta. In the next 40 to 50 minutes, you're gonna hear a rapid fire of all challenges that you're gonna run into when you turn an LLM into real LLM serving infrastructure. There's gonna be a lot of content, so sit tight and let's get started. I guess since 2023, everyone is in this AI gold rush, trying to find compute resources to fit the unprecedented growth from big models and longer contexts. This year, the demand keeps growing because test time compute and compound LLM system are the new hotness. Scaling LLM serving is almost becoming building like a distributed operating system. It's so foundational to all of the innovations. And we are seeing innovations happen everywhere, especially at the intersection. At Meta's AI Infra, we are building this strong foundation to empower our researchers and ML engineers. So a tiny bit of myself, I've been solving the problems of serving models for the past 6 years. My current focus is cost saving and DevX. LLM serving is probably the most interesting model serving problem that I work on. Because the model is a system. The best solution really requires you to think comprehensively to get some joint optimization between model, product, and system. And part of the 0 to 1 launch that bring Meta AI online, our team optimized inference backend for Meta AI and smart glasses. Apart from the public-facing traffic that everybody sees, we also have a lot of internal traffic, like RHF, data curation, distillation that goes into the making of Llama family of models. These are absolutely massive. And during the busy week of RHF, our team has to process like hundreds of millions of examples. And about 3 months ago, I shared our story at the AI Infra at Skill conference. The most question that I got is, should I run my own LLM service? How do I optimize my own inference? Sorry. A little spoiler. I think the best way to answer this question is to build everything step by step. Well, let's imagine we have an awesome product idea. We are going to build a web agent that's browsing InfoQ's website. And every time Charlotte posts something, you're going to summarize it, push it to your customer, and let them ask them follow-up. What an awesome idea. So we're going to go through a journey of 4 stages of challenges. But let's start with the simplest one. You get the model, you get some hardware. What to do next? Step 1, you need a model runner. LLM inference is notoriously expensive to run. The model is trained with next token prediction, which means your inference logic is also token by token. So look at this colorful sentence. If an LLM has to generate it, every color switching means another model forward pass. We call the generation for the first token preview and all the tokens after the first decode. This iterative process is very challenging to accelerate. Normally, the end-to-end latency is going to be a few seconds. That's why almost all LLM application is using streaming interface. To tackle this special execution pattern, you want to find a runtime that at least supports continuous batching and KV cache. Why continuous batching? So the response from LLM will have variable lengths. The shorter one will exit earlier if you're just using a static batching or dynamic batching, and the resource will be idle. What is continuous batching then? Well, imagine like a bus At every bus stop, which is the end of each decoding step, it will try to pick up new passengers if there's an empty spot. And the new passengers carry a lot of luggage. They're very slow, get on the bus. It's just like preview. And the bus will keep going if nobody is waiting at the bus stops. And fortunately, most of the bus stops are indeed empty, just like was in the South Bay. This is how we keep GPU well utilized. What about KV cache them? So every decoding step is conditioned on all previously generated tokens. The K and V tensors for the same token at the same position basically stay the same across the single generation request. If you don't do this, your attention computation is gonna be cubic instead of quadratic, which is beyond sustainable. Luckily, almost all of the mainstream LLM frameworks support it, and you wouldn't go too wrong here. Step 2 is to find some hardware. The high-end data center GPU today typically come with 8 GPU setup. This is an example from Meta. You will see some network connectivity with different speed, but our job is fitting. So let's only pay attention to HBM size. You will see some 40, 80, 96, 192. These are the numbers from the most popular data center GPUs like A100, H100, MI300. Let's take some H100 and try to fit some models in. The 8B models fitting one GPU just fine. You get the runner, you can just run it. 70B model cannot fit in one GPU. We use tensor parallelism to partition the weights across multiple GPUs on the same host. You need at least 2 GPUs to not womb. And typically, we do use 4 to 8 GPUs to allow bigger batch size to improve the throughput, because the KV cache does take quite an amount of memory. The 405B model can fit in 8 H100. The weights is gonna take over 800 gig under BF16, so you will need 2 nodes. And we recommend using pipeline parallelism to further partition the weights across the nodes, because communication for multi-node tensor parallelism is just gonna introduce too much overhead. But you can also choose MI300, which offers you 192 gig of HBM, and you can serve it on a single host without going through all the troubles. Okay, so the takeaway is, don't just grab your training or eval code, find some runtime specialized in LLM inference serving, and try to have some understanding of your AI hardware that match your model. And you can use tensor or pipeline parallelism to fit your models. Okay. So we solved the fitting problem, and the product is hooked up. The next challenge is, it's too slow. Well, most infra problem does get better by throwing capacity. You can also throw more GPUs, like 3 million of GPUs on the screen, or you wait for faster next generation GPUs if you can actually wait. Throwing capacity blindly only take you like this far, not that far. So you're staring at the runtime that you find and thinking, outside of this 100 arguments, is there anything that I can tune to make it faster? Well, certainly there is, but let's understand where is the limit. Remember we mentioned that LLM inference consists of preview and decode. Preview generates the first token. It reads a huge model weight, and it does tons of computations across all of these tokens within your prompt to find all the relation between each pair of tokens. And it then output one token. Decode generates subsequent tokens Again, it reads a huge model weight and it reads all the KV cache, but it only tried to attend next token, one next token to all previously generated tokens. And the compute density is a lot lower. This makes prefill GPU compute heavy, decode memory bandwidth heavy, and the KV cache requires quite an amount of memory capacity. To sum up, making LLM faster is really about fitting this LLM mass operation within these three types of system resources. And they scale with the model sizes, sequence lengths, batch sizes, but a little annoying that they scale with different multiplier. However, the ratio of the system resources on your hardware are fixed once it's manufactured. This is why we have to try harder to bridge the gap. Where do we start them? Well, when you say things are slow, let's be a little bit more precise. If you're using a streaming interface, you might care about the first token latency, or TTFT, to reduce the awkward silence when your customer is waiting for something to be generated. Or you care about the generation speed, or output speed, or TTIT or TTOT, they're all the same. This is to let your user to see your app is super fast, churning out the responses, or you actually get a bunch of, it's not user-facing, and it's a bunch of bots talking to each other. In a non-streaming use cases, you might actually care the end-to-end latency because your client has some timeouts. These three latencies can be optimized in slightly different ways. And you need to set up reasonable expectations around what's achievable for your model sizes, input-output lengths, and your own cost budget. For example, you cannot expect a 405B model to run faster than a 70B model unless you can make significant modification to your hardware. Okay, so with this context, we can get back to our step one, throwing capacity about a little more wisely. I actually ignored the fact that even in continuous batching, you will see some holes right there. This is because when running prefill in the continuous batch, all of the decoding steps in the same batch will get slowed down. This might be okay because practically, per instance, request per second for LLM is quite low because of the resource demand. So most of the steps are actually not interrupted. Imagine you suddenly get a request with 32K input. All of the decoding will get stuck for a few seconds, and your customer will actually see it. They will feel it. We can fix this problem with disaggregation. We replicate the already partitioned ways, and we run prefill and decode in different services. This way, we can scale their system resources separately and get rid of this annoying 10x P99 latency for your decode. That's because P99 is basically the average of your prefill latency. It helps us to maintain the same latency SLOs with much fewer machines. If you only rely on 8-way tensor parallelism, even with DSAG in place, if you're looking for processing an input that's 128K, you are looking for at least a minute. If your app does look for this type of responsiveness, even for such long input, you do have the expensive option to use context parallelism that further partition the entire workload at the context dimension. It helps you to store more targeted compute at your prefill time. Replication and partition are our best friends. It helps us to manipulate the system performance profile into a better shape that can fit into the hardware that come with different shapes. Whenever something is too big to functionally fit or create a substantial system bottleneck, we'll just cut it, copy it, and we can get over it. Okay, enough about distributed inference. Let's move on to step 2. You should consider make your problem smaller. As long as your product quality can tolerate, let's try to make some modification to lower the burden for your hardware. Number 1, well, just use more concise prompt. Number 2, get a smaller model with specialized fine-tuning, distillation, or pruning. Number 3, apply quantization to unlock twice or even more compute available on your hardware. And pay attention here, quantization is not a single technique. At the post-training time, you can mix and match different components, different D-type, or different policy to use for quantization. The tremendous openness in the LLM community actually will allow you to find implementation for all of this very easily. You can play around and see which option gives you the best ROI. Step 3, we can also get better at memory management using caching or virtual memory. So remember we discussed that KV cache takes quite an amount of memory. This problem can be basically tackled in the same way in the traditional system performance. First, we'll try to identify what can actually get cached. For requests using roleplay or integrity check, you typically have to throw a very long system prompt to keep the model in context. And for multi-turn chatbot application, each request includes all of the chat history from previous turns. That's a lot of recomputation. And on your GPU server, there's a decent in-memory storage system right there. You will get half terabytes of HBM, a few terabytes of DRAM, a few dozens of terabytes of flash. We can build a hierarchical caching system that actually match the KV cache usage pattern. For example, the common system prompt might get cached in the HBM. The active usage chat history that you need to kind of load every minute or so can sit in DRAM. Chat history from less engaging users can be offloaded to flash. If you can manage the system and privacy complexity for this type of problem, this is basically a no-brainer. It's lossless. And you can see it's very common for us to see over 50% of reduction for both latency and capacity. Step 4, if you're looking for even more levers on performance and cost saving, you can try speculative decoding, chunk prefill, dive deeper in the attention kernels, or try some sparsity around at the token level. There are tons of LLM domain-specific optimization. This table is like a quick glimpse into this space. Each technique takes different trade-off, sometimes conflicting trade-off, around TTFT, TTIT, quality, and cost. And you need to decide what's important for your product. And you also want to take my words with a grain of salt, because the exact behavior really depends your own unique workload. Okay, let's recap what we've learned so far. Getting the basics right will give you a 10x foundation. Distributed inference, smaller input and model, and caching will give you another 2 to 4x boost. You are free to explore more advanced decoding algorithm, changes in your engine to find your next 10x or 100x. Okay, people might come and ask, hey, Charlotte, this sounds so complicated. Did you do all of this at Meta? You will find out what we might do if you hear the next two challenges. Suppose our awesome InfoQ agent is fast enough for product launch. What to solve next? Our toy system now has to turn into a production service that is available for a user at all times. What comes to your mind when you hear the word production? To me, everything could function in a slightly unexpected way. We get a lot more moving pieces. Request distribution is changing. Like you can see in this graph, you get users with different intent of engagement, while some just like spam you a lot more often. The input and to output ratio has bigger variance. The effective batch size are much smaller and also changes a lot. All of this invalidate our assumptions around create that perfect ratio of system resources to max our hardware ROI. And what's more, the temporal patterns is also changing a lot. We get daily peaks, daily off peaks, and spikes, just like all online services. And the spikes might be just some random people running evals. Very strict real-time online services, like chatbot, is not the only type of upstream for LLMs. Like human-in-the-loop annotations is also real-time, but it has to align with the evaluator's schedule. And batch processing for summarization and feature generation can be scheduled with some time shifting up to minutes or hours. What's more, LLM deployment has very complex latency and throughput trade-off. Throughput is only meaningful when it can meet your latency SLOs. And you have to do this for multiple deployments. A mature product typically involves serving a handful of LLMs. You get the main big model for your chat, and you get a bunch of ancillary models for safety, planning, rewarding, function calling, etc., to complete the end-to-end loop. Putting everything together, you'll often find the peak flaws, the hardware vendor advertises kind of useless. It's very common to lose 50% effective flops, even at the earliest kernel benchmarking stage, especially for shorter input. And combining the latency bound and some operating buffer, you're gonna lose 10x. This is very common. How do we get back all of these losing flops? Step one, let's think harder what can be traded off. Out of quality, latency, throughput, reliability, and cost, you can probably only get to choose 2 or 3 of them. I want you to ask this question to yourself. Do you really need 3 nines or 4 nines if that's gonna cost you 3x? Do your customer only feel meaningful differences when you are serving at an output speed of 100 tokens per second versus 10 tokens per second? Well, as a reference, I'm only speak at a speed of 5 tokens per second. After you thought through it, you come to me and say, hey, Charlotte, I just want to push harder on the latency. Tell me more about inference optimizations. Wait a second. Let's look at the data and decide where to optimize. You get the 7TB model running at roughly 200 milliseconds on a GPU, which is a pretty decent performance. But your service is only hosted in California. Your New York customers get another 75 milliseconds in network round trip. And you don't just hard code your host name and port. Another 75 milliseconds goes into naive host selection, house check, load balancing, and everything else. Your LLMs may be multimodal. And you have to download the images in the request, another 150 milliseconds. Your app has to coordinate a bunch of business logic, adding safety checks before and after the main model call. And it might also do a bunch of other things like fetch information, rack, doing search. This can easily add another 400 milliseconds. So look at this distribution. You can tell me where to spend time, where should we optimize? Hold on. You actually care about stuckness from this long preview. And then let's do the stack. Earlier, I made this stack sound so simple. You just create 2 services, and everything is done. Your preview operations and your decode operations is gonna get nicely batched together. What I didn't mention is the link between preview and decode is quite thin. And between preview and decode, you have to transfer hundreds of megabytes of KV cache. You typically have an upper network bandwidth limit when you are talking TCP/IP. It's very common to add another 50 to 100 milliseconds to your TTFT if you're doing this stack. This means by doing this stack, you are basically signing up for these hard optimizations like request scheduling and overlap data transfer and compute at every single layers. You might also want to do a little bit of additional tuning based on your own unique network environment. And what's more, how would you push a binary to it? How would you update model weights? That alone probably needs a full 40-minute session to explain. So not this stack. Maybe caching is easier. True, but LLM has this annoying positional encoding. The same tokens showing up in the beginning of the sentence versus the end of the sentence will have different embedding. So imagine you're trying to get the mod cache, but you are sending requests including the last 10 messages from your customer. Then nothing will be cached. So to improve the cache hit rate, you not only need a big cache, as we discussed how you can build a hierarchy, you also need prompts that are very cacheable. To solve this problem, we co-designed the chat history management with our product team, and we even further customized the request data flow to not only maximize cache hit rate, but also leave longer inference latency budget. To route these requests to the host with the cache, we use consistent hashing to sticky route the request from the same session to the same host. And we also have to ensure that retries on host failure are also sticky. Okay, maybe we can try quantization then. If you are in a resource-constrained environment, you really don't have a choice, and quantization is basically a functional requirement. But when you do have the choice, you might want to be a little bit more paranoid. What we commonly see is you quantize the weights to FP8, you run some benchmark, let's say MMLU. The scores are the same, sometimes even higher. When you release the quantization to production, suddenly your customer just showing up and say, something is not working. Most of the benchmarks are saturated and may not best represent your own product objective. You should build your own product eval and use a slow roll process to get these wins. Speaking of slow roll and testing, how do we maintain these nice scores over time? You know, inference bugs can manifest as subtle performance degradation because LLMs are probabilistic models. So it's possible you have something horribly wrong, but the result comes out still decently correct. To prevent your models from getting dumber over time, our approach is no different in traditional CI/CD. Just make small benchmark run every single one of your diff and run more comprehensive ones on every release for inference engine. Okay, another time for takeaway. We will lose theoretical flops in production environment a lot. Don't get surprised about it. And when you look at the end-to-end inference, end-to-end latency, inference is, a lot of time is just a small portion of it. And if you want to make good use of KV cache and the persistent KV cache, you often have to do product and infra co-optimization. And lastly, don't forget to continuously evaluate and test all of these acceleration techniques directly using the signals from your product. Okay, our InfoQ agent is a big hit. We decided to make it a little bit more fun. We want to let our users to customize which speakers they want to subscribe. What else gonna change? This is when we encounter our last stage of challenges, which is scaling, which is a never-ending topic for all infra engineers. You get so many rocket parts, they're scattered around. How are we gonna put them together to make them fly? To assess that, let's ask ourselves, what numbers will get bigger as you scale your apps? We will have more deployments. We will use more GPUs. We will involve more developers and serve more models. Let's look at this one by one. Step one, we get more deployments. Let's use DSAG as an example because I like it. We mentioned prefill service need more GPU compute. So you find a hardware called hardware P uniquely fit this job. And decode service need more memory bandwidth. So you find a hardware D for this job. But when you look at the host in the data center, region 1 is full of hardware P, and region 2 is full of hardware D. Interesting. Remember, prefill and decode has to transfer hundreds of megabytes of data to each other for every single request. So you probably don't want to do that cross-region. This means if you opt in for disaggregated deployments with some hardware preferences, you actually need to maintain and optimize inference deployments not for 1, but for 3, because you also need to handle the remainders. Thinking about this, you might have different answers about what's your net wings gonna look like here. Remember the idea of using context parallelism for very long input. It helps you to reduce the TTFT. 90% of the time, you're at this happy path. You get high bandwidth network from RDMA, and everything is fast and nice. However, faulty GPU in one partition will take down your entire process group. Assuming at any time we have 3% random failures for your GPU cards, the blast radius will exponentially grow when the smallest inference deployment units is getting bigger. What's more, with faster interconnect, these hosts are required to be actually placed physically closer together. And whenever there are some maintenance events going on in the infra, like network device upgrade, daily maintenance from the data center, all of these hosts will be gone at the same time. At Meta, we actually have to create like a dedicated job scheduler to allocate hosts for distributed inference. We also talk about heterogeneous hardware, heterogeneous deployment, and hosts with shared fate. What about auto-scaling? In the CPU world, if you have a service with changing workloads throughout the day, you will find a throughput metrics like QPS or your request queue size. Then you turn on auto-scaling and you forget about it. For LLM, number one, the right throughput metrics is extremely tricky to find because the bottleneck depends on your workload. QPS obviously does not work. Tokens per second works under a lot of caveats. And number two, you cannot freely upsize, as you're likely running into the GPU limit first. Putting allocation challenges together, you need a deployment allocator to place your job with awareness of network topologies and the maintenance events to minimize the impact from the infrastructure activities. To tackle heterogeneous hardware and auto-scaling, you will need a deployment solver that actually treats auto-scaling as a shard placement problem. It understands the supply and demand from your inference services, and it can make decent decisions even when the demand exceeds supply. At scale, all of these traditional operational problems are all solved with quite sophisticated software and algorithms. We talk about allocation at scale. Step two is cost saving. Okay, so the last 35 minutes cover dozens of options to make things faster and cheaper. It's gonna be quite tedious to manually apply every single one of them and tune every job individually. When you draw a graph of latency and throughput for different serving options, like different number of GPU, different inference acceleration techniques to try, you will get a graph looks like the left. You will see the lines eventually crossing to each other at some point. This means your best cost-effective option actually depends on your latency requirement. So we have to categorize these workloads to create like an inference menu to really allow our customers to choose the best for them. This type of inference menu requires very extensive performance benchmarking automation and a lot of data science. Suppose we solve the volume problem. Cost saving also has to be looked at end-to-end, just like latency. Your tool chain will get so much more effective if you grab some knowledge about inference accelerations that I talk about from this talk. I commonly hear people raise this question. Hey, look at this workload. Look at the gaps between the off-peaks and peaks. Can we run something else to leverage this free capacity? It's like, wait a second. This green line is your provision throughput, and you can actually raise this line like 3x by applying some ideas I mentioned in this talk. This is good to hear, but I have many deployments. Where to start? A common perception I see from people is 90% people focus on 1, 2, 3 head models because we think that deployment consumes all of the GPUs. But when you actually measure, you will find so many tail deployments than you can imagine. And collectively, they might consume even more GPUs than your main model. This means observability and automation are no longer nice to haves. They directly help you to claim all of this low-hanging fruit. To put them together, remember the 10x loss. Your ideal throughput is determined by your workload and your hardware. The inference optimization will help you to improve achievable throughput. The deployment option you choose yourself is gonna determine your provision throughput, which you might not choose the best that's available for you. And you want your deployment to be sized automatically, as you are charged by GPUs, not by tokens when you're hosting your dedicated deployments. With good data foundation, and also removing some foot guns from our customers, we are capable of really minimizing the gaps across the four. Next step, running a product is beyond serving one version for each model. You want to split your traffic and evaluate a few launch candidates. And this has to happen for multiple models on the platform. What does this mean? Everything we discussed so far got yet another dimension to add to actually multiply onto all of the problem set. And this is a good time to summarize what we've learned. You've already got a glimpse into all of the building blocks for a scalable LLM serving infrastructure. We start from model and hardware, which are really the spotlights for everything. To fit the model onto hardware efficiently, you will need a good model runner, a performant execution engine with a handful of inference acceleration techniques. To get the engine ready to become production service, we need to think about end-to-end latency, efficiency, and correctness by investing into monitoring, routing, product integration, scheduling optimization, and continuous evaluation. A serving infrastructure needs to run multiple LLM services. This is when allocation, deployment management, model management, experimentation all come into play. And we haven't even talked about quota and interfaces. Look at this graph. Model and hardware are really just a tip of the whole LLM serving iceberg. To get the best of all worlds, we often have to do vertical optimizations across the entire stack. All right, I think we spent a good amount of time scratching the surface of LLM serving infrastructure. I hope you find something useful from this talk, and hopefully you can get some insights for your inference strategies. Many of the pains are still very, very real, and I hope to see more innovations to help us scale development and deployment for GenAI applications altogether. This is everything I have. Thank you, everyone.
Hello, hello. Wow, that was an amazing presentation. As you can see, it's a big iceberg that we have to work through for dealing all these interesting scaling and latencies across the networks and data centers. So thank you for that, Charlotte. Questions. So we have a few minutes for questions. So if you want to raise your hand, I'll run the mic to you. Anyone? All right, while you think about that, let me ask Charlotte a question. What are you focusing on right now? Obviously, there's a lot of areas, but just currently, what is one or two areas that you're focusing on at the moment?
I'm getting ready for the next generation of Llama, obviously.
Okay. 3.5, I guess, or what's the toughest challenging that in this space that you worked on in the last, 6 months or a year?
I think for model serving, especially if you want to get things end to end, it's not like you only care about modeling, or you hire a bunch of GPU experts, or you hire a bunch of distributed system experts. You actually have to have all of the three, and you actually have to make these people talk to each other and understand the trade-off in the same language. Because a lot of time when you get things online, you cannot, there's only limited stuff that you can do by only applying infra techniques. Sometimes you do have to make some modification to your models directly. So you have to work closely with the modeling people, ensuring that the modeling direction can get manifest into the correct, net behavior from all of those techniques together. And as I showing here, yeah, a lot of time people will say, hey, LLM serving, you have a lot of interesting problem to solve. Yeah, but still around 70% or even 80% of the time have to be spent in typical system generalist type of work. We're just we have to build this foundation very solid, make sure it's scalable, debuggable, especially. Yeah.
Makes sense. Thank you. You have questions here.
So I have a couple of questions. I was just curious, at your peak times, what was your maximum GPU utilization that you have gone through? And also the second was, in terms of hardware performance specifically, so do you work with vendor partners like either NVIDIA or AMD to even make it more better in terms of acceleration techniques? I mean, they may be providing libraries to even give better performance of using majority of the hardware resources. And how does that fit in your work here?
Yeah, that's a great question. First about GPU utilization. So it's actually quite complicated to use one single metric to measure your GPU utilization, because GPU is this very massive parallel machines. There is this, for NVIDIA hardware, there is this device active metric that you can get, but that metric is kind of, it's very coarse. It tells you if anything that's happening in this GPU. It doesn't measure at a finer grain, how are you utilize everything there? Because for a single GPU, there's hundreds of processing unit within it. We also have a processing unit, a metric to measure the utilization at the processing unit level. So typically in our work, we do cover all of those as well. And the exact GPU device utilization and the streaming processors utilization really depends on your workload. Typically, we do see them go up to more than 50% very easily for L1 workload. But sometimes if you're only looking at the utilization, it can get misleading from time to time. Like we mentioned that applying caching, your tokens per second will go up, but your utilization will actually go down. and this is, you need to make sure you're tracking the stuff that you care about. So for the second question about working with hardware vendor to improve performance, so Meta is a quite big company. We have people working on, the more an internal cloud LLM serving platform. We are also partnering very closely with PyTorch. So we are basically collaborating together, making sure, let's say we first introduce AMD to our fleet. We work very closely with the PyTorch team. They get the signal directly from the fleet to know, are the features all covered? Are all of those operators running? Even today, I think there's still a tiny bit of gaps. They get the signals, they get both kernel level performance as well as the end-to-end performance, and they are indeed working closely. That's the exact partnership is outside of my own expertise.
All right, thank you, Charlotte. We ran out of time, so you can find her maybe toward the end of the hallway here, but I want to make time for the next session. So let's give another hand for Charlotte.